Okay. Daily physics problem number 2, whatever. You got a hoop oriented on a horizontal plane with a string of some sort suspended within the hoop, tightly wrought, whatever, it's in the problem. Anyways, there's a bead on the string and it falls between what's labeled P1 and P2. And you have to find out velocity and time, and it's nigh impossible, and the problem doesn't make any sense at all. Anyways, the trick is that the bead is falling at a constant rate in accordance with gravity. So its acceleration will be constant throughout the entire fall regardless, at what we all know is 9.81 meters per second squared. But it's not actually 9.8 meters per second squared because the bead is at a slant. Gravity is operating completely downward, straight vertical, G. It'll be represented by that, whatever. You can see the G, right? Okay, yeah. You can see the G, but, so, gravity is only going to be operating, part of gravity is only going to be affecting the actual bead. You know, the whole right triangle thing, we worked with it in physics last year, where you have theta, an angle, in between two lines, and if this were gravity, you know, the straight vertical one, then this would only be part of it, or the actual vector that whatever your object's along, in our case the bead, is only part of gravity, so it becomes cosine theta gravity. And so the acceleration of the bead is cosine theta gravity. Oh, shit. Oh, yeah, okay. Alright, so the acceleration of the bead is cosine theta gravity. Anyways, the real trick of the problem is that the time it takes for this bead to fall between these 2 points will be exactly the same along any point around the entire circle. It doesn't matter, because the acceleration of the bead is changing proportional to this angle here, to this angle with the vertical axis of the hoop. If the same string was suspended across the entire hoop and the bead was made to fall directly down the hoop, then it would fall at the whole 9.81 meters per second squared of gravity, because it was completely vertical. So this is where the trick comes in. Bam. Sorry, had to get more goddamn paper. Anyways, so, the radius of the circle is r, and we have a kinematic equation that allows us to solve for things, you know, velocity, acceleration, we can deal with time, whatever. That I lost. Oh, here it is. Okay, kinematic equation. Theta x is equal to velocity initial times time plus 1/2 acceleration times time squared. Yeah, you can see that, right? Okay, yeah. Anyways, so theta x, well, let's say that the bead was aligned with the vertical center of the hoop, so it's going to fall all the way down the vertical center of the hoop, whatever, right? So that distance, we suddenly know that. We know a part of the equation that we never did. We know 2r. And the velocity starts at 0. Fuck that. Okay, so that's 0 plus 1/2. I explained earlier that the acceleration of the bead along any point is cosine theta g times time squared. Well, since it's vertical, you can still see that, right? Okay, yeah. Well, since it's vertical, it's going to be cosine of 1. Or it's going to be cosine of 0, because there's no angle relative to the actual vertical center and the string we now have set up here, because it's just 0, so whatever. Cosine of 0 is 1, so we can eliminate that from the equation entirely, and then you're just left with 2r is equal to 1/2 g times time squared. So, little basic algebraic manipulation here. I'm running out of paper space. 1 second. Shit. Anyways, save that last line in your brain for a second. Okay, little basic algebraic manipulation. You get 4r is equal to g times time squared, divide the g over. 4r divided by g is equal to time squared, so we square time to get rid of that exponent, and that reduces to 2rg r square root equals time. So the time along any point in the circle for a bead to fall on, whatever, is that. It's 2rg. It's irrelevant of the actual distances between P1 and P2. It just has to do with the circle and gravity, the radius of the circle and gravity. So that's how you solve for time, which you actually have to solve for first. So the problem is given out of order, which is kind of annoying, but then it's kind of simple from there to get to velocity, having your time, because we have another kinematic equation. You've all seen it. I'm just going to write it down. Velocity is equal to velocity initial plus acceleration times time. So velocity final when it reaches point 2, that's 0. We know it starts at initial, so it's irrelevant to the equation. Cosine theta g as earlier, because even though we know that time is constant along the entire circle, the velocity that we're looking at in this specific problem is actually still at an angle. We don't know theta, but it doesn't matter. It's just going to stay a variable. So v is equal to cosine theta g times time, which we now do know is just add it up there. 2 square root of r over g. Anyways, so that's your time figure. And then you do a bit of algebraic manipulation, and you're going to get that the velocity is equal to, what do we got here? Velocity is equal to 2 cosine theta g times square root of r over g. Yeah, that's right. Yeah, it should be right. Alright, that's it.